Good morning, Mr. Stat Sensei, Mr. Spensei, and we are going to go over two sample proportions. And today we are actually going to write a hypothesis test, or we're going to conduct a hypothesis test for two sample proportion. And there are a lot of things to keep in mind on this, in that it's a little bit different than what we've done before. So an automobile manufacturer randomly assigns 850 cars to two distinct assembly methods. So we have random assignment. That's interesting. That means I don't have to worry about the N is less than 10%. All right, to two distinct methods, 350 cars were randomly assigned to the first method, resulting in 28 with defects. So it looks like we have N is 350 and with 28 with defects. We have 500 cars assigned to the second method, producing 32 defects. Is there enough evidence at 10% to indicate that the second assembly resulted in fewer defects? So let's take a look at this. Let's start recording some information down that we know. Well, we know that we had 350 cars assigned to the first method, and that first method had 28 with defects. The second one had 500 cars assigned with 32. So this is going to have a 28 over 350. So 28 divided by 350 is 0.08. So about 8% of the cars had defects with that method. But over here, we have 32 divided by 500. 32 divided by 500 equals 0.064. So we can see right away that method 2 had some fewer defects. The question is it statistically significant? So that's why we have to run a hypothesis test. So what's my null? Well, my null hypothesis is that there's no difference, that P1 equals P2. The alternative is that the second one had fewer defects. That means the first one had more defects. So we need to define our parameters. We have two of them. Let P1 equal the true population proportion of cars with defects from method 1. All right. Now we probably should say assembly method 1, but we're trying to keep it short. Let P2 equal the true population proportion of cars with defects from method 2. All right, we have a new formula. Technically, when we're working with proportions, we pool. Now the calculator does it automatically behind the scenes, but we still have to show the formula, and we still have to do that. Now you like to use PC. Now that's P pooled really, but I like to use PC, and here's my formula. So this is P for P's combined, and it's X1 plus X2 over N1 plus N2. All right? Now there's a good reason for all of that, and the reason is, hey, you know what? We took this from a sample, and if we combine them together, it'll give us a better estimate because we believe that they're the same. The claim is that they're the same. So if they're slightly different, we combine them together, we should get the same thing. All right, a better estimate. So in this case, PC equals, our numerator is going to be 28 plus 32, and our denominator is going to be 350 over 500. All right? I like to go ahead and cheat at this moment. All right? So I'm going to go ahead and write down the other formula that we need, and we will go from there a little bit. All right. Actually, you know what? No, let's continue with this, and I'll show you the cheat method here in a moment. So 28 plus 32, that's my numerator. My denominator is 350 plus 800, or excuse me, 350 plus 500, which is 850, but they told us earlier in the story that it was 850 to begin with, that they sampled 850 cars. So we have 60 defects out of the 850. So my best estimate is 0.0705. So PC is 0.0705, and we have to have that in order to do our conditions. So what we have is, first condition is random assignment. It's not a random sample. This is random assignment. Oh, and this is method 1. And this is method 2. Need to keep what, all right, so random assignment of 350 cars. Method 2, random assignment of 500 cars. So that takes care of that. Next thing is a combined one, and that is we have two independent groups, or two independent samples. I'm going to call them groups. I feel more comfortable with that. All right, two independent groups. So that's good. The next thing is we need to worry about the NP and NQ, but instead of it being what it's, we have to use PC now. So this is going to be N1 times P hat C and N1 times 1 minus P hat C. All right, well, P hat C is 0.0705. So in this case, we had 350 times 0.0705. Here we have 350 times 1 minus 0.0705. $350 times 0.0705, that's 24.6. That's greater than 10, we're good to go. 350 times parenthesis 1 minus 0.0705 is 325.3, and that's also greater than 10, so we're good to go there. The next one, we have to do it for the other side. We have N2 P hat C and N2 times 1 minus P hat C. N2 was 500, so 500 times 0.0705. Five hundred times 0.0705 equals 35. And that's greater than 10. And then 500 times 1 minus 0.0705 is 464.7. And that's greater than 10. So we know it's large enough to use a normal approximation. And then we get to our formula. And our formula is Z equals P hat 1 minus P hat 2 over P hat C times 1 minus P hat C over N1 plus P hat C times 1 minus P hat C over N2. So we're looking for the probability that Z is greater than, well, we said P hat 1 is 0.08. So 0.08 minus 0.064. And we said P hat C is 0.0705. So 0.0705 over, our sample size for 1 was 350. And I'm going to go ahead and subtract that. 1 minus 0.0705. And that gives me 0.9295. So then plus 0.0705 times 0.9275 over my sample size of 500. All right, let's go ahead and calculate this. So we're going to go to stat test. And we're going to drop down to 2 proportion z-test, which happens to be number 6. And we had 28 with method 1 out of 350 cars. And the second one had 32 defects out of 500 cars. And we had a greater than for our alternative hypothesis. So we want to make sure we're consistent there. We're going to go ahead and calculate. And this is where I said we could cheat earlier. Look, we have P hat 1, we have P hat 2. We got this right here, this P hat is P hat C. And we also have our P value of 0.1850 and a Z score of 0.8963. 0.89, so we want the probability that Z is greater than 0.8963. And it turns out that that's 0.1850. So 0.1850, and I need to flip back. And it told me an alpha level of 10%. Well, this is greater than an alpha level of 10%. So in this case, we're going to fail to reject. So our P value is 0.1850. We fail to reject the hoe. There is not enough evidence. There's not sufficient evidence at alpha equals 0.10 to suggest that method 1 has more defects than method 2. That method 1 has more defects than method 2. Or we could have said that method 2 has fewer defects than method 1. All right? Or so that the true proportion of defects from method 1 is less than or is greater than that for method 2. All right? And probably that's what I should say, that the true population proportion of method 1 defects is more than method 2. All right. Well, I appreciate you watching. I hope that helped, and I hope to see you on the next one. Thank you.